In this video, we will discuss an algorithm that achieves approximate agreement in an asynchronous network. Recall that, when the network is asynchronous, we do not know when messages get delivered. This means that, if a correct node has not yet received a message that it expects, then there are two possibilities. Either the message is delayed or the sender of that message is Byzantine and the message was never sent. We will be working in a setting of n nodes in an asynchronous network. Out of these nodes, f are Byzantine. Each correct node has a real value as input. Recall that approximate agreement requires the correct nodes to output, for any positive predefined error epsilon, values that are epsilon close and that are in the range of correct inputs. These two properties are called epsilon agreement and correct range validity. We know that, unless f is lower than 1/3 of n, approximate agreement cannot be solved. Our goal is then to achieve approximate agreement in an asynchronous network, as long as the number of Byzantine nodes f is lower than 1/3 of n. Our algorithm will run multiple iterations. In each iteration, the correct nodes will distribute their current values, and they will compute new values based on the values received. This approach should ensure that the values held by the correct nodes get closer and closer with each iteration, so that epsilon agreement is eventually reached. In addition, we want to make sure that the values remain in the correct inputs range. Since there are n-f correct nodes, we can guarantee that, in each iteration, each node receives n-f values, out of which at most f are corrupted. This means that at most the lowest f and the highest f values received are outside the correct inputs range. Then, if we discard the outliers, namely the lowest f and the highest f values, we have at least one value left. And every value remaining is in the correct inputs range. Each node may compute its new value as the average of the highest and the lowest values remaining. We would like to guarantee that, in each iteration, every two correct nodes end up with some common values after discarding the outliers. This will ensure that the range of values held by the correct nodes gets halved in each iteration. And then, if the correct inputs are between some values a and b, the base 2 logarithm of b minus a divided by epsilon gives us a sufficient number of iterations to achieve approximate agreement. So, for the remainder of this video, we will focus on designing a strategy for the nodes to distribute their values, so that every pair of correct nodes ends up with some values in common even after discarding outliers. Our first attempt will rely on plain broadcast. In each iteration, each node sends its value to all nodes. Then, as there are n-f correct nodes, each correct node may wait until it receives n-f values, and may afterwards discard the outliers and compute its new value as the average between the lowest and the highest values remaining. Does this strategy work when f is lower than 1/3 of n? Pause the video for a moment and think about it. This strategy fails when f is lower than 1/3 of n. In fact, it also fails when f is lower than n divided by 4. To understand why, we will look at 5 nodes, out of which 4 are honest and 1 is Byzantine. We will only look at one iteration. 2 of the correct nodes will have input 0 and the other 2 will have input 1. The Byzantine node sends -1 to the correct nodes with input 0 and 2 to the correct nodes with input 1. The correct nodes may only wait until they receive messages from n-f nodes. Hence, due to the asynchronous communication, it is possible that 2 of the correct nodes receive the values -1, 0, 0, and 1, while the other 2 receive the values 0, 1, 1, and 2. Then, the correct nodes compute their new values as the average of the lowest and the highest values remaining after discarding the outliers. Note that the correct nodes maintain their inputs. The same may happen in the next iteration and in all further iterations, which means that epsilon agreement is never reached. The strategy that the Byzantine node used was to send different values to different parties. We can prevent this strategy by replacing plain broadcast with reliable broadcast. Reliable broadcast ensures that, if a correct node receives some value from a Byzantine node, all correct nodes receive the same value eventually. Now, the correct nodes will wait for n-f values sent via reliable broadcast. Keep in mind that this does not mean that they receive the exact same n-f values. Does our new algorithm work when f is lower than 1/3 of n? Pause the video for a moment and think about it. Our algorithm still fails. To understand why, we can look at a setting of 4 nodes, out of which one is Byzantine. The 3 correct nodes have inputs 0, 1 and 1. We will only look at one iteration. The Byzantine node will send -1 via reliable broadcast. Since the network is asynchronous, it could be that the correct node with input 0 is the first that receives this value. The other correct nodes eventually receive this value as well, but only after they stopped waiting because they had already received n-f values. So, one correct node receives the values -1, 0, 1. The other 2 correct nodes receive the values 0, 1, 1. Then, the correct nodes end up maintaining their input values once again. This problem would be fixed if the nodes could announce to each other that there are more reliable broadcast invocations that are worth waiting for. So we will now try that. When a node receives the n-f values via reliable broadcast, it will not stop waiting just yet. Instead, it will report the n-f values received. That is, it simply sends these values to all nodes. Even after reporting these values, nodes will still keep receiving values via reliable broadcast. If a correct node reports a value, all correct nodes receive it eventually. This is one of the properties of reliable broadcast. This means that eventually, each correct node will receive every value reported by some correct node. Once a node sees that some other node has reported n-f values that it has also received via reliable broadcast, it marks that node as a witness. And once a node has marked n-f nodes as witnesses, it can stop waiting for values. It has now received enough values, and now it is ready to compute its new value. Let us now discuss why this works. First, we need to ensure that eventually each correct node marks n-f nodes as witnesses, and therefore computes a new value. Pause the video for a moment to think why this is the case. This is because each correct node can be marked as a witness. Recall that, if a correct node waits long enough, it receives every value reported by some correct node. This is guaranteed by reliable broadcast. Then, let us take a look at 2 correct nodes that have marked n-f nodes as witnesses. They have at least one correct witness in common. Pause the video for a moment to think why this is the case. Since there are n nodes in total, the intersection of the 2 sets of witnesses will contain at least f+1 nodes. Out of these f+1 nodes, at most f are Byzantine, and therefore at least one is correct. Next, there are n-f values that both of the 2 correct nodes that marked n-f nodes as witnesses have received. Pause the video for a moment to think why this is the case. The 2 nodes have a correct witness in common, and this correct witness has reported the same n-f values. This means that both nodes have received the n-f values reported by the correct witness. And finally, since the 2 nodes have n-f values in common, they also end up with a value in common after discarding the outliers. The 2 nodes compute their new values as midpoints of intersecting intervals that are included in the range of correct values. This means that the distance between the 2 midpoints, and hence the difference between the new values of the 2 correct nodes, is at most 1/2 of the size of the correct values range. Since this happens for every pair of correct nodes, the correct values range gets halved in each iteration. This way, we have achieved approximate agreement in an asynchronous network, given that f is lower than 1/3 of n. In this video, we have discussed an algorithm achieving approximate agreement in an asynchronous network. The algorithm achieves optimal resilience. The core of the algorithm is the witness technique, which enables the nodes to distribute their values so that every pair of correct nodes ends up with n-f values in common. Thanks for watching this video.